just point it at me. Just counting away. Just keep pointing at me. Right. Okay. Okay. I want to present Boscovich's unified field theory.
Just the arrow, right arm.
There we go. So, first of all, this person has given us quite a few problems.
This is your biggest problem.
I like his hairstyle. Right. There is actually various different theories of relativity, and before Einstein, there was Poincaré-Lorentz theory, and then it was the Einstein 1905 theory, then it was the Minkowski theory. The Poincaré theory says there's an ether. Einstein 1905 says there's no ether, and Minkowski decides that time is the fourth dimension. And this is oversimplification because there's actually many more theories of relativity. Right. So, first of all, Einstein believes this in 1905. Then Minkowski gives a lecture and he says, I've got a better theory than Einstein and Poincaré. And in the lecture he explains that time is to be treated as the fourth dimension. So that's Minkowski's theory. And so, first of all, Einstein says, oh, that's wrong. Minkowski's not right. Minkowski's wrong. So, I think Minkowski then died quite young, and later on, Einstein decides, okay, Minkowski was right, time is the fourth dimension. Now, the way the mainstream treats it, Einstein is good to change his mind, and he changes his mind on very many number of occasions. But it does cause a bit of confusion here, because Einstein 1905, that's his theory, and he's first of all saying that's different theory to that one. Yeah? And then he changes his mind. So really, it's Minkowski's theory of relativity. It's not Einstein's theory of relativity. But we're all honouring Einstein's that. So, and the problem with treating time as the fourth dimension is, well, if you're treating time as the fourth dimension, like space, but why not go backwards and forwards in time the same way you go backwards and forwards in space? So it creates that sort of problem. And it opens the possibility then for the exotic things like time travel, space-time warpage, and everything else. So it is really another assumption, in a way, and it's causing you how to treat the maths, how to interpret it. So there you are, the situation then like before Einstein-Minkowski theory. And Einstein saying no ether. He then later on in life changes his mind a bit more and he says, well, the ether exists. I was wrong to be right in 1905. And you're saying to yourself, well, what does that mean? He's now saying the ether exists, and his 1905 theory says it doesn't. So he's really talking about this theory now. So the way I look at it is it causes a great deal of confusion. Einstein's changed his mind, so what theory is he really talking about? What is it? And it's just confusing. And of course, I think you pointed out there are different versions of ether. So it's caused a great deal of confusion, and I've sort of like argued with lots of different people. And one person I argued with was saying, oh, I can prove such thing in special relativity. So you naturally think, oh, Einstein theory 1905. But when I challenged him, said, well, actually, you're talking about things which are dealt with in Poincaré theory. And then his answer to that was, well, the history of special relativity is quite a bit of a mess. So it is confusing because people can say special relativity and they're not really referring to that theory, they could be referring to that one. So it's confusing. So it causes a lot of problems. Right, this is Poincaré, and he first introduced the term the principle of relativity, and that was long before Einstein. So you could treat in the principle of relativity as being the start of relativity. The first person to use that term, and it's Poincaré's theory. So we'd be obviously honouring the wrong person then, calling it Einstein's theory. So next one. He was a great guy. I like this guy, Galileo, and he actually talked about relativity as well. And of course, it's a different version to what Einstein was talking about. But if you're honouring the person who first talked about relativity, well, surely it should be Galileo's relativity. So another version of relativity. What I'm basically trying to point out, there was a long tradition of relativity before Galileo. And when it comes to talking about relativity, this long tradition of dealing with relativity before Einstein gets mostly ignored. There's too much emphasis on Einstein. So this person is a Catholic priest and a scientist, and in the 18th century the science he was looking at was what Galileo had left us. So he was looking at relativity as well. And the problem with Galileo was he went before the Inquisition, and the Inquisition then afterwards banned the Copernican revolution and books on it. So as a good Catholic, you were not really supposed to study Copernican revolution anymore. But he was part of this person here, Father Boscovich, was part of the Society of Jesus. He was what you call a Jesuit priest, and they make a vow of total loyalty to the Pope. So he was exempt. He was allowed to study things that were forbidden to ordinary Catholics. And this here is the Boscovich curve, which I'll be getting back to later. So I should have really put a picture of Newton, but I haven't. Right, so Newton came along. In England, it was a Protestant country, and Newton was still allowed to carry on looking at Galileo and Kepler's physics sort of thing. And he wasn't under the control of the Catholic Church saying don't study those things. So it came along with Newtonian physics. And Father Boscovich was the person who persuaded the Pope and the others to lift the ban on the Copernican revolution enough so that Newtonian physics could be taught on the continent of Europe and all the other Catholic countries. So he really was the first Newtonian on the continent of Europe. Now, with the Catholic churches, was not enough to just have an incomplete version of physics. And what Newton left us was the Principia, and he left a load of queries at the end, like 30 queries and so forth. So it was really an incomplete theory. The Catholic Church was not really prepared to accept an incomplete theory. So Father Boscovich was the first person to provide a unified theory based upon Newtonian physics. So the next important book after Newton's book on Principia was Boscovich's book, A Theory of Natural Philosophy, which is a unified theory of Newtonian physics. And this gets mostly forgotten about. Right. So, despite most people in the physics community forgetting all about Boscovich, he is still remembered in the history of physics departments to some extent, and they do have conferences on him. And I went to a conference on him last year, and it was in Pavia University, and Boscovich is famous there. So they decided to do a survey of people in that area to find out if anybody had heard of Boscovich. And well, the only person who had heard of Boscovich was a person who thought it was the name of a street. So he's so famous that he's not even known about in the place where he is famous. And that's where he is at the moment. And I have a copy of A New Scientist in 1958, written by Dr. McKay, and he says in this New Scientist article, it says 60 years ago, Boscovich was considered one of the top scientists, the equal of Newton, Leibniz, Euler, and Franklin. And so the historians were putting him up in the top 12 greatest scientists of all time. So now, if you look at Father Boscovich, 100 years from when he was in the top 12, well, he's not even in the top 100 anymore. He's disappeared completely outside. And that's how bad physics people are about remembering their history. Right. So he's been mostly ignored by physicists, and he's only become something of historical interest. And so I say the unified field theory is Boscovich's theory, which is a unified theory of Newtonian physics. So, this is one of the people at the conference I attended last year, and he's a professor of chemistry, and he teaches his students that Boscovich is a unified field theory as well, and he explains to his students that that quantum physics came from Boscovich, and he's got articles published on it and other things, and there's also books on it. But he's in where Boscovich is famous is an area called Yugoslavia or Croatia or Serbia. So he's in that area, and Boscovich has got an institute named after him. He's got a statue, and he's got a museum. So he's famous enough to have those sort of things. And so you've got these people who are aware of Boscovich's contributions to physics, and they're not really getting in much publicity in the science area in the West. Okay. Right. Oh. Right. This is another person. He's also in that area where Boscovich is famous, where hardly anybody knows him, and he's got his PhD in Boscovich's theory, and he's the person who organises conferences. And one of the things I think I overheard him said was he publishes papers and nobody ever reads them. So that's how famous papers on Boscovich's theory are. Right. This is the Boscovich curve. Now, when they looked at Newton's theory, they realised it wasn't complete. And one of the problems with Newton's theory was gravity. Gravity was only attractive force. And trying to explain the whole of creation by just an attractive force didn't really tie up to things. So Boscovich is dealing with the force changing from being attractive and repulsive. So the force is supposed to be following this sort of curve. Okay? So what happens is, one moment you've got the force acting in that direction, next time it's acting in that direction. So what you're forming is places where the attractive and the repulsive force are stable. And so that is a balance. Now that idea was used for forming the electrons going around the nucleus of atoms. So from this you have allowed and forbidden orbits of the electrons. And you got Thomson, I think it was Lord Kelvin, who was writing about that, and you had Niels Bohr, who was also building a Bohr model on that. So this is the beginnings of quantum physics. And this force curve is supposed to apply to on the large scale and the small scale, so it applies further up. So what they point out that it does modify gravity on the large scale, modify Newtonian dynamics. Now, next. There you go. This is Boscovich, it's like one of their notes over there, as their number one scientist, the top scientist equal of you, that ends up on their notes. And this is the diagram, what he's done about the force law being applied to the orbits of electrons around the nucleus. And this is it. This is the planetary model of Thomson. And I got this, we got this from Dragoslav, one of his slides. So you get the book on this, is the Corpuscular Theory of Matter, 1907. So we go, suppose we regard the charged ion as a Boscovian atom, and the Boscovian atom is a point particle, exerting a central force on a corpuscle which changes from repulsion to attraction and from attraction to repulsion several times. So you've got the nucleus there, force curve, and allowed orbits, and then areas where it's forbidden. The basis of the chemical atom. Okay. So basically Boscovich gives the origin of atomic physics, and in the Catholic Church they usually honour him as the father of atomic physics, and people like Niels Bohr and Heisenberg and the others who were working on the Manhattan Project and so forth were saying, and honoured him in lectures and so forth, saying that what they were working on was atomic physics as coming from the father of atomic physics, Boscovich. So this was known until all the emphasis then went on to the quantum revolution, the Einstein revolution. Everything's kind of pushed forward to looking at things which we saw like coming from 1905 and forgetting things before that. Okay. So in my travels, I've tried to attract many people to unified field theory. Other people are already on there. And this is one of the people I've contacted. It's Augustus, for instance, is a young, when he was a young man, he used to be a young picture, and he was from Brookhaven. So he's looked at the Boscovich curve and worked out the mathematics of it, and it is a Fibonacci sequence, and this is the right Fibonacci. So if I were to show the picture again of the curve, but I think you can remember it, that curve is following Fibonacci sequence. The forces are obeying Fibonacci sequence. So, how we construct the Fibonacci sequence, there's several ways of doing it. If you consider a pair of rabbits, they give birth to 2 rabbits, and those 2 rabbits can give birth to more rabbits. it, so you've got that kilograph around it, and that kilograph stays around it, so you get ending up sequence one pair, add them together, 2 pairs, and so on. So it's a number sequence going 1 plus 1 equals 2, 1 plus 2 equals 3, 2 plus 3 equals 5. So this is a sort of like natural number sequence in nature. And you can form things like this spiral which follows that sort of like number sequence. And of course when you look in nature, you find that it is following, well, it's following that spiral which is based on the Fibonacci sequence. Nature is following it. You've got the spiral again. So nature, for some reason or other, likes the Fibonacci sequence. And when you look in articles, you can find Fibonacci mentioned in some other places. And I brought this one down as an example. There's an article on the internet by someone dealing with investments and says, can Fibonacci numbers forecast your financial future? A lot of investors believe that Fibonacci calculations can give you insights into stock market movements. So people are seeing this pattern everywhere. So it is basically, how could somebody like Father Boscovich work out a unified theory in the 18th century before anybody did any experimental results, experiments on this sort of thing? Or he just thought it through from his perspective, and he looked for patterns. And it is the Pythagorean way to do things. You're looking for patterns. So that's how he came up with it. He looked for the pattern which would fit into give a unified theory. So it's not really based so rigorously on pluralism. You do the theory, then you work out, then you do the experiments and see whether it fits into what you've worked out. So what we have is Newton's theory led to Boscovich's theory, and Boscovich came quantum and relativity theories. Boscovich's theory was called Newtonian physics. I don't think I'll emphasise that enough, that Galileo started the relativity thing, and that prompted Father Boscovich then to look into it as well. So he was dealing with relativity. And from Boscovich's perspective, I'm translating this book now from Latin and so forth, it's not being thought of as important. From Boscovich's perspective, it was, what if there's a length contraction, and what if there's a time dilation? And his conclusion is, there must be a universal speed. So Einstein did it the other way around. He said universal speed, therefore length contraction and time dilation. So how are you going to classify relativity theory? Which way around do you want it? Really, Boscovich was dealing with it long before 1905 and long before Poincaré, and it goes back to Galileo. Boscovich's theory was called Newtonian physics, so there was no real reason to change it from Newtonian physics. You had a unified theory of Newtonian physics, and it led to dealing with relativity, and it led to dealing with the orbits of electrons around atoms, and it led to quantum physics. Physics as a human enterprise is just building on mistakes. Falsehoods are taught to physics students. And only as one example, in the case of special relativity, students are told the falsehood that the Michelson-Morley experiment gives empirical proof of special relativity over Newtonian physics. It doesn't. Because if you're a physics student, they go through some of the thought experiments of Einstein, And then a student, if you're sceptical, would say, well, what proof have you got? And they will usually say, some more of the experiment. So they're lying. Right. So Professor Norton, who's a historian of interested in Einstein, points out the Michelson-Morley experiment was considered by Einstein as giving support to principle of relativity and not to the constancy of light speed. Okay? So how do we classify Einstein's theory? He talked about two assumptions, the principle of relativity and the constancy of light speed. The Michelson-Morley experiment only shows the principle of relativity. It doesn't show the constancy of light speed, so it's not showing special relativity. So straight off, the student is lied to. And now, the principle of relativity, minus the light speed there, comes from Galileo. And that is still part of Newtonian physics. So the Michelson-Morley experiment agrees with Newtonian physics, and therefore cannot support the claim to use it to change to another theory. So it's a fundamental problem there. Not only don't we know what Einstein's special theory of relativity is, the experiment that is supposed to support the change doesn't. When all the mistakes are accounted for, special relativity turns back into becoming just Newtonian physics, and the speed of light in vacuum as being a constant is a mere convention. I'm going by point carry on that, on conventionalism. That's my understanding of it. It's just Newtonian physics. So there we have it. Einstein believers have convinced themselves to believe something that just is not so, which they admit looks nonsense. So when they first introduce the student to Einstein's relativity, they admit the thought experiment looks nonsense, usually. And they initiate newcomers in believing the same nonsense by their false representation of the facts. Now, it's not just Einsteinian physics and so forth that had problems. Newtonian physics has also got loads of mistakes in. So when I'm talking about Newtonian physics, I'm really usually not meaning only the popular theory, which is Boscovich's theory. Hence, Einstein's stuff is a diversion from the proper physics, a unified theory, which is Boscovich. So, that's, I can carry on and waffle for ages, and I thought I'd stop there now, in case anybody's got any questions. One question.
Yeah. It's not so much a question to start with, it's a comment.
Yeah.
You say that Newton had queries in the Principia, he didn't. He had queries in the optics.
Optics, yeah.
Yeah. Also, you imply that Newton only considered attractive force because of gravity, but he also considered repulsive forces as well.
Yeah, but he didn't have a unified theory on that.
Well, I'm not concerned with that.
Yeah.
I'm saying he had repulsive forces as well.
Yeah.
I'm saying that there's a whole tradition of Newtonian physics of looking at attractive and repulsive forces.
Yes, the modified Newtonian dynamics.
No. In the 18th century, stemming from Newton.
Yeah.
Of which Boscovich was the most sophisticated example, but certainly not the only example.
Yeah.
So I think you've got to look at the whole historical context.
In the historical context, it was Boscovich.
No, he was one person. No, he didn't start it. He gave the most sophisticated theory, but
Yeah.
he didn't start it.
Yeah.
There was a tradition of many people doing that kind of Newtonian physics. Boscovich was the most sophisticated theory and had the biggest influence.
If you look at Newton, you can say, well, really he was working on ideas from, say, other people like...
No, I'm not concerned with that. I'm just saying...
When it comes down to the publications,
No.
the most important book we consider to be Newton's Principia.
So when you're talking about historical things, you have to look at the whole picture. And you can't just single out this and say, we're going to forget everything. As you did with this, you have to do with...
Well, I'm pointing out the trend. The trend was, you've got Galileo, you've got Kepler, you've got Newton, and you've got Boscovich. And these those sort of like books were considered very important and influential. And you've got other people working on those things, but they get forgotten for the main trailblazers.
Let me interrupt. You have essentially 5 minutes left and 5 minutes for questions.
Can I just ask a question as we're going to? What evidence is there that the atom has this Fibonacci structure? I know that you say not that there is this Fibonacci structure in the atomic forces.
Well,
I don't think there is evidence for that to my knowledge.
It is how historically the electron, the atom, the Bohr atom and that were constructed. But you had allowed and forbidden orbits, and it was based upon that.
Well, they weren't
the
Fibonacci.
maths for the sequence has been worked out now by one of the people I'm in contact with. This is Augustus Prince.
Okay. Yeah. Believe it.
And other people worked it out the same thing. Okay.
So as I said, you mind your time. You would like some other questions, and you have a total of 10 minutes, including questions.
What, 10 minutes left?
You have 10 minutes left.
Okay. Any more questions? Right. Yeah.
The 10 minutes was to include your part 2.
I don't mind missing out part 2. And it's too more controversial. Okay.
It's true that the Michelson-Morley experiment does not prove the second postulate because the alternative is Reed's emission theory, which denies this postulate.
Yeah.
But there are independent there are independent experiments which confirm time dilation effect and which are incompatible with Galilean kinematics.
Yeah.
So,
No, it doesn't.
with Newtonian physics.
What it means, if you look at the Michelson-Morley experiment, you can construct maths based upon the principle of relativity, and one way of doing it is constructing it with light speed as constant, and the other way of constructing it is with light speed not constant. And so you've got two sets of maths, and they're tied together. If you can use one set of maths and something else, then you also tie the other bit of maths to it as well.
I don't know how this answer relates to my
So it means that those
question. Yeah?
so it means those can be transformed as well. You've got
How about the experiments confirming time dilation effect?
well, from that, when the time dilation thing, that is based upon the perspective that light speed is a constant. So if you're not taking that perspective, then to compensate for that, then light speed will have to be variable. So it's the way you're looking at the experiment.
It is just the consequence of relativity theory.
Sorry?
The time dilation effect is just a consequence of relativity theory and not of Newtonian theory.
But it depends how you're treating the speed of light. In Newtonian physics, if you start from Newtonian physics and you've got the maths written down and you're saying, right, I'm going to plug in the speed of light now as being constant, and that's going to have a knock-on effect by then having time to change. So it's just the maths. But if you're going to say, instead of doing that, I'm going to have time as universal between people, then the knock-on effect of that is light speed is going to be changing. It's all just a consequence of whether you want to treat light speed as universal or not. And that's how you're plugging it into the maths.
I'm afraid that your answer at best is not direct.
And I just can't see them up to go to that.
Very indirect.
So I construct that equation. So based on the principal relativity, I get that. And you've got C prime, T prime, and you've got C without the prime, and B and T. Now, if you want to assume that light speed is constant, then you're setting that is equal to that, and as a consequence, the time is going to be different. But if you're assuming that light speed isn't constant, then you're setting that is equal to that, and then speed of light is varying. So it's depending on how you're doing it. This is just Newtonian, what you get from Newtonian physics. Okay? So that is how you're doing the experiment. This is what you're assuming as you do the experiment. Okay. Okay. If we've got, how much more I've got left?
4 minutes.
4 minutes. Right. Right. How do you go back?
Up arrow. The left arrow. Arrow pointing left. Oh, you can do it that way.
Click on the one you want.
You just scroll down that. Scroll down that.
Yeah. Slideshow. Yeah. Right. Right, what you can consider is a box with light moving from one wall to the other. So light's moving from there to there, speed c, and that's moving, the box is moving at speed v. So for an outside observer, he's saying speed is c plus v, and this is straightforward Newtonian physics. So eventually, through considering that in that direction, and the opposite, when light goes the other way, it's c minus v. You form that equation. And that's where when I started, I didn't assume that c prime was equal to c. So I just formed that straightforward from Newtonian physics, and you get that equation. And so the next step is saying, is light speed a constant or not? And so then you're plugging in, say, whether c prime is equal to c, or whether t prime is equal to t. In fact, this comes straight forward from Newtonian physics. So everything from 1905 is based upon people making lots of mistakes, both in Newtonian physics and within Einstein's and quantum revolutions. And people not taking into account the unified field theory which started in 1758. And of course other people were working on it, but the person who gets credit for doing it first is Boscovich, and the historical records put down, the book is being published, I think, in 1758. So that's when the unified theory, or based upon Newtonian physics, was published. The historical record. Other people working on it can usually be traced back to working on the same sort of ideas as from Boscovich himself. And it's looking at Fibonacci sequence, natural patterns in nature. Controversial enough? The end.
Okay.
Thank you.
Time for a question.
No. It's done.
Okay, let's thank him again. We'll move right on to the next speaker.
CY low.
CY low.
Very interesting. I heard about the history of unification. Now I want to talking about the real thing. The unification, what Einstein proposed it actually works.